Alright, so now that we were kind of happy with our ideas around div and grad and curl, it's time to put together pretty much everything that we've been doing so far to look at the three big theorems which link together everything that we've done and give us, in many cases, easier ways to calculate the crazy integrals that we've been doing up to now. So the first one that we want to have a look at is Green's theorem in the plane. So we know that the fundamental theorem of calculus links together the idea of a derivative and an integral. And it basically says, or one particular version of it says, if you take the derivative of a function and you integrate it from a to b, it's the same as just looking at the function value at b minus the function value at a. And we saw a little while ago that we have something similar for a conservative vector field on a curve c from a to b. So if we're looking at the line integral, we have something similar. So here is our conservative vector field, which, since it's a conservative vector field, we know that we can express it as the gradient of a scalar field, and we're taking the dot product of that as we go around a curve, and it is the same as just looking at the value of the scalar field at the end and start points and subtracting. So that was kind of the idea of path invariance that we saw when we were looking at line integrals. So Green's theorem is a two-dimensional version of expressing a double integral as a line integral. So we're really looking at derivative of a 2D vector field and linking it, linking a line integral and linking a double integral. So although it might sound weird as I say it, we will see that there is a similarity with the fundamental theorem of calculus. Specifically, we are looking at a 2D vector field, so just a vector field with x and y components, no z component, and we're thinking about some closed curve. All right, so what is the intuition behind Green's theorem before we actually state it? Well, we've talked about the circulation of a vector field around a curve, and we know that it's given by this formula over here, and it's kind of a measure of how much the vector field lies around that curve. So you're looking at kind of the components of the vector field along each bit of the curve and adding them all up. And in some ways this kind of describes the macroscopic behavior of our vector field. So if you want to think about our vector field describing water velocity in a water flow, then our circulation really says if you have your water flowing in whatever crazy way and you look at one particular curve, how much water is actually flowing along that curve. So you might only have a little bit, or you might have that in fact your water is circulating around that curve. So it's a measure there. So that's the one part of Green's theorem. The other part is going to look at what we can think of as the microscopic behavior of a vector field. So we know that the curl of the vector field at a point measures basically the tendency of our vector field to circulate around a tiny little curve centered at each point. So we could kind of think of our curl as, like, at each point, like how much is our vector field circulating at each of those points. And as we saw, we've just got a two-dimensional vector field, but we can calculate the curl, and that's what this looks over here, like over here. So we've seen that already. And the key thing about Green's theorem is it links these two. And it says that if you look at the macroscopic view, so you look at the line integral going around a curve of this vector field, it's the same as if you look at the curl, so the little microscopic ones, if you add up all those curls, you will get the same thing. Let's put that into something tangible. What I've just said is that if you look at the macroscopic value around a line integral. So remember here, this is what we get if we look at f dot dr. So this really says if you take the line integral of your vector field around dr, that's going to be equal to, well, this bit over here is actually just the curl. Well, it's the magnitude of the curl, because our curl looks like that and it has a k component. So what this bit really says is it's the curl dotted with k, because that's just going to end up giving us the magnitude. So we've got our macroscopic behavior here. We look just by going around without thinking about what's going on inside the region. And over here, we look at everything that's going on in the region, all the little curls, we add them all up, and the net result is that these two things are equal. So what is the fine print? This formula holds if, well, C is an oriented boundary, so we do have to be aware of which way around we're going, of some region which is considered as a surface, and we're orienting that surface so that it has a normal in the k direction. So we kind of need that because that's the direction of all our little curls. Practically speaking, what does that mean? It means our curve is oriented with the region that we're thinking of on the left as we move around C in the direction of its orientation. So if we head back to the pictures that we've got, notice if I'm standing anywhere on the boundary here, the direction I walk is the direction so that I make sure that the region is on my left. So if I'm standing here, then facing this way, the region is on my left. So I would walk in this direction. So this is why we had to talk about orientation. It might have seemed a little weird at the time, but we need it to be able to talk about these theorems. Okay, and if we are oriented so that when we move around the curve, the region we're interested in is on our left, then we call such a curve positively oriented with respect to that region. And if you're just a simple closed curve bounding a region, then your curve will be oriented counterclockwise. So you can see that, so if we're thinking of this whole area here as our region, then walking around the outside will be anticlockwise. On the other hand, if you have a hole in the middle of the region, if you think about how you have to walk around that hole to make sure that you keep your region on your left, then in fact you have to walk counterclockwise. Okay, I mean, you have to walk clockwise, sorry. Okay, so counterclockwise when you're going around the outside, but if you're in any holes, then you'll be going clockwise around those. Other things that you might notice when we think about this, so let's just move off some of those marks. If we want to think about the unit tangent to our curve, so if at any point on our curve we can have a tangent vector, unit tangent vector, which we know how to find. Remember, if our curve is parameterized as r of t, then our unit tangent vector, we find, well, dr by dt will give us the direction of the tangent vector, and then you normalize that. So, I mean, you create a unit vector. So let's do it like this. I have a tangent vector there, and we'll get a unit tangent by, let's call it unitizing. Okay, so we're going to need that in a moment. Okay, so we've got our unit tangent vector wherever we are, and we can also think about our unit normal pointing out. Then what we end up with from the way that we've oriented everything is that if we take the tangent crossed with our k, which we're thinking of k as pointing out, so our z is pointing out this direction, will equal our normal. So this is just to kind of talk about the orientation. Don't get too hung up on it. Okay, so as we've just seen, you might see Green's theorem written like this, but usually we're going to use it in the form that we saw it over here. So let's in fact dive straight in and see why this might be a great theorem, because it's not clear why we would want this, but have a look at this. Okay, so we would like to evaluate this, so we can see this is a line integral, a closed line integral of this crazy thing over here, where C is the positively oriented boundary of the quarter disk Q. Okay, so we want to find this line integral. Let's have a look at what our region is. So there's our x and our y. So it's a quarter disk, so x squared plus y squared needs to be less than a squared and bigger than 0. X is bigger than 0 and y is bigger than 0. Okay, so we've got, whoops, a quarter disk like so, of radius a, and it's positively oriented, so that says if we're walking along the boundary, then we need to always keep the region on our left. So we must be orienting it this way. Okay, so here's the region that we're interested in. Okay, and we would like to find this line integral. So we would basically integrate, if we were going to work out this thing here, we would integrate this along this curve there. But Green's theorem says actually we can make life a lot easier for ourselves. So just let's remind ourselves of what it looks like. It says if you have something that looks like this, a line integral, then you can treat each of these components really as components of a vector field, and you can instead do this integral over here. Does that make life any better? Well, we're going to treat, so this is going to be our x component of our vector field, and this is going to be our y component. So we have f1 is equal to x minus y cubed, and f2 is equal to y cubed plus x cubed. And Green's theorem says that our integral, this crazy thing here, must be the same as the integral over the region that we're interested in of df2 by dx minus df1 by dy over the region. Okay, well, this becomes something quite nice. This is going to become integral over the region, so df2. So we want this differentiated with respect to x, so that's going to give us 3x squared, and then we're going to subtract off the derivative of this with respect to y, so that's going to be plus 3y squared. And suddenly this is starting to look like a much nicer integral. I mean, we know really what to do with this. We can see, pulling out the 3, what we've got is the integral over this whole region here of x squared plus y squared. And at this point I hope that you immediately think, polar coordinates might be useful here. So let's switch. So we know that r squared is equal to x squared plus y squared. We also know that in polar coordinates our dA is r dr d theta. And if we want to think about what are our limits of integration, because we're integrating over this region. Our radius is going to go from 0 out to A, so r goes from 0 to A. And if you want to think about our theta measures from theta is 0 all the way to here, so theta goes from 0, whoops, not 2 pi, pi over 2. So if we put that all together, what do we get? Well, our integral is now 3, and we're going to replace this with r squared. We're going to replace our dA with an r dr d theta, and we'll end up with, that gives us an r cubed dr d theta. And we can pick our order of integration because our limits don't depend on each other. So let's do r first. I'm going to go from 0 to A, and then I'm going to do theta going from 0 to pi over 2. So finally our integral is pi over 2. So this integral over here is 1 over 4 r to the 4 from 0 to A. So here I've got 3/4, whoops, A to the 4 from 0. Now I've just left integrating d theta. So finally that's 3 over 4, a to the 4, and that'll be times pi over 2. Because when I integrate this, I just get theta, and it's going to be pi over 2 minus 0. So if I put that all together nicely, I get 3 pi a to the 4 over 8. Okay, I've done that a bit quickly. Please check it. Let me know if I've made a mistake, but I think it's fairly straightforward. The key to all of this is notice that we've gone from having this crazy thing over here, which was a line integral of a vector field, which is a little more challenging to integrate, to something really straightforward, just this thing over here. And that really is the power of Green's theorem, is it often helps you translate quite complicated integrals into things that are straightforward to do. So let's have a look at another example. So here again, we've got a complicated line integral, and we want to integrate it over this curve that's shown in blue here. So it's a trapezoid that we put like that. Okay, well, we can do exactly the same trick. Let's see what happens here. So we treat this, that is our x component of our vector field. This is our y component. So f1 is equal to x sine y squared minus y squared. So we're going to need the derivative of f1 with respect to y. That's going to be 2xy cos of y squared minus 2y, and f2 is equal to x squared y cos y squared plus 3x, and we're going to need the derivative of f2 with respect to x, so that's going to give us 2xy cos of y squared plus 3. And now Green's theorem says, well, this integral is in fact equal to the integral over our region of this bit minus this bit. Okay, let's do that subtraction. So we've got our integral over our region. So we've got this term subtracting off that bit, so those will cancel, and then we've got the 3 minus 2y. So we get 3 plus 2y. Did I do that correctly? Let's just check. Yes. Okay. So now we really, again, are just left with a fairly straightforward integral. You could decide how to do this. My suggestion would be to think about chopping the integral into slices like this. So we need to know what each of these limits are. So our x limits, x will go from 0 to 1, and our y limits, well, this line here is the line minus 2 plus x, and this line over here is the line 2 minus x. So our y is going to go from minus 2 plus x to 2 minus x. So we can plug that in, and we're going to integrate y first. So we're going to have 3 plus 2y dy dx, and we're going from minus 2 plus x to 2 minus x, and then our x limits from 0 to 1. And you can finish that off, but again, pretty straightforward. So again, we've taken a complicated line integral, and Green's theorem has just told us straight off, simplify things, turn it into a nice surface integral. So that is the power of Green's theorem. There are other theorems in the plane that are in fact roughly equivalent to Green's theorem. So for example, you might see the divergence theorem. Let's have a quick look at what that looks like. So that says that if you look at the divergence of a vector field over a region, that's going to be the same as looking at the overall, the dot product of our vector field with the outward normal around the loop, around that region. And if you think about it, it's kind of doing the same macroscopic, microscopic thing that we did before. So this bit over here is really saying, okay, let's see how much of the vector field points outwards as we go around the loop. So it kind of gives a macroscopic divergence kind of idea. And that's equal to looking, well, remember our divergence gives us what's happening at each little point. How much is our field diverging, or I guess streaming out at any particular little point, and we're going to add all of those together. And if you add all those little divergences together across the entire region, then the overall divergence there, that sum of divergences, is going to be equal to this macroscopic divergence. So it's kind of, it's analogous to the curl idea. And in fact, if you have a look in the textbook, it uses Green's theorem to prove this one. So this is our divergence theorem, and again, useful in swapping from possibly from complicated line integrals to more straightforward surface integrals. Okay, so that is the first of the big theorems, and I hope it makes you feel a bit better. Now you're probably not going to have to do as many line integrals in your life because you can use Green's theorem. So where do we head from here? We're going to have a look at the divergence theorem in 3 space, and then finally, which is also sometimes called Gauss's theorem, and then we're going to have a look at Stokes' theorem. So 2 more videos coming up, but for the moment, just practice a few examples of using Green's theorem.